So back again at the General Assembly with Yohai Kaspi of the Weizmann Institute in Israel, who is a co-I of the Juno mission, who was just at this very interesting press conference. And nobody really talked about this aspect of Juno's mission, and that is the physical structure of the atmosphere. We didn't really cover that too much. We were talking about the core. But what about the red spot? What have we learned about the aspects of the physical characteristics that amateur astronomers can see from their own backyards? That how has all that changed from pre-launch to 10 years after?
Yeah, thank you for the question. So the amateur astronomers and the kind of known picture of Jupiter that we have is that we see these red and white stripes, and of course the storms, and the most famous one, the Great Red Spot that you mentioned. Now, before Juno, we knew that these storms are connected to the wind structure. So we basically have jet streams, just like on Earth, but we have multiple jet streams going east-west with velocities reaching 3 or 4 times faster than the Earth, and the storms are embedded within these jet streams. With Juno, with the gravity measurements that we talked about regarding the interior, we've also been able to see the gravity signature of the winds. So that allows us to pin down how far these winds that we see at the surface or at the cloud level go down into the interior of the planet. And we learned that these winds go down 3,000 kilometers beneath the cloud layer. So 3,000 kilometers is a lot, but this is compared to the 70,000 of the radius of Jupiter. So a few percent in radius and about 1% in mass. So when you think about Jupiter and look at it, you can think that about 1% of the mass of Jupiter is moving back and forth in these jet streams. Now within that, we have the storms. And the Great Red Spot was actually targeted by the Juno mission in 2 orbits, in orbit 18 and in orbit 21. So we set the orbit such that we fly right over the Great Red Spot, and we measure the Great Red Spot both with the microwave instrument that we mentioned before. This was also in orbit 7 done, and then in the orbits 18 and 21 with the gravity measurements. And we learned from that the Great Red Spot, which is an anticyclone system, like a storm in the atmosphere, goes pretty far deep. We saw it in all channels of the microwave radiometer, so that means it goes down a few hundred kilometers deep. But in terms of the gravity signature, it's not deeper than 500 kilometers. So we kind of pinned down this thing to be somewhere between 300 and 500 kilometers. If you think about
in depth, I mean, that's that's a lot. I mean,
so that's a lot of depth.
Yeah.
Still, if you think about the size of it, it's about 20,000 kilometers across.
Right.
So 20,000 kilometers across, and say 100 kilometers in depth. So still a pancake, if you want, a very thin one, but a very massive storm, much, much more massive than the things that we see here on Earth. And that's why the storm survived for so many years, unlike storms on Earth, which survive, say, days to maybe a week.
Let me ask you a very basic question. So prior to launch and now, how do we understand the layers of the atmosphere, starting off at the atmosphere and going down as deep as we possibly can with your instruments? In other words, how would you describe, because Jupiter is not like any other, it's not like a terrestrial mass planet with an atmosphere. Saturn may be similar to some extent, a gas giant, Uranus and Neptune. But how could you describe Jupiter from the top of the atmosphere on down? And I hope you understand my question.
Yeah, you're absolutely right. Jupiter and all the giant planets, as you mentioned, they don't really have something that we can define as an exact atmosphere. We're going down up from something with a very thin density, and then gradually growing up, orders of magnitude, where in the interior we have densities reaching tens of megabars. Okay, so we have about 8 orders of magnitude from the cloud layer down to the interior. If I want to define this and kind of try and address your question, when we look at Jupiter from the outside, what we see is the cloud layer. So we see ammonia clouds, and ammonia condensates at 0.7 bars, roughly. So that's the first features that we see. These are these white clouds that we see on Jupiter with a red background. Then we go further in, and at about 6 bars, we have condensation of water. So That's an important layer in terms of the thermodynamics of Jupiter. These are the temperatures where water condensates. How do we know that? Because we know roughly the structure, the temperature structures from the outside towards the interior. I mean, we know at which densities and temperatures these properties condensate. Then we move further inward. We can't see with our naked eye, but we can see with the microwave radiometer, which has 6 different channels at 6 different depths. And from that, what we learn, as Scott mentioned before, is that Jupiter is complex. The atmosphere is not well mixed. What do we mean by that? It means that different regions have different composition of these elements. If you think about Earth's atmosphere, then if I'm breathing here in Vienna, and if I'm breathing in some other place in the world, the composition of the atmosphere is still the same. I have 76% nitrogen and 23% oxygen and some other elements. Maybe one example is that water vapor is not equal in every place. I have less in desert areas and more in, say, tropical areas. But most of it is well mixed. On Jupiter, that's not the case. We see with MWR that it's not well mixed as we might have thought before. Then we go deeper, and the next maybe important level is the 3,000 kilometer level, and that's where these winds that we see stop. So they don't, though the winds and this what we call differential rotation doesn't go that deep.
It doesn't go below 3,000
Yeah.
kilometers in depth from the top of Jupiter's atmosphere, is what you're saying. Okay.
That's actually also the place where the electrical conductivity rises. So Jupiter, because it's a fluid,
The electrical conductivity.
and the reason is that we have a fluid which is rotating, which is creating a gigantic magnetic field of Jupiter. So we have the conductivity, something that's rising from the interior towards the outside. At about 10,000 kilometers, the magnetic field really kicks in and affect the dynamics. That is still uncertain, but possibly what's kind of damping down the wind has to do with these magnetic field and dissipation that we get from that. Beneath that, when we reach 1 bar, so we're talking here 7,000 kilometers deep, that's where the fluid goes from being molecular, hydrogen and helium, to being metallic. So at that point, it becomes so dense that it becomes ionized. So the molecules are so tightly compacted.
Did you say one bar, or you mean 1 Earth atmosphere?
I said one. No, I said 1 megabar.
1 megabar.
Oh, I said 1 bar. Sorry. Yeah.
You mean 1 megabar,
At 1 megabar, that process happens.
which is 1 million
which is
Earth
about
atmosphere.
it's about 1 million Earth atmospheres, or 7,000 kilometers deep. That where it becomes ionized. So then it turns into this different kind of material than what we had towards the outside.
And just for reference, we know what 1 atmosphere is here on Earth. Venus has 92 bar, and missions to Venus have all been hamstrung by it's only at 92 bars. Imagine what 1 million bar, if you were at 1 million bars on Jupiter, imagine.
Yeah, absolutely. You
Incredible.
cannot survive that. I mean, we have one example. We have the Galileo probe that dropped down. It was designed to go into high pressures, and it survived to about 22 bars. Okay, so not even the Venus kind of pressure.
That's pretty incredible, though, the fact that it did survive.
Absolutely, and this is back in the 90s, and this is with dropping it from an orbiting spacecraft. And then going back to your question, we go deeper beyond this 1 megabar level. At some point, helium condensates, and we have what's called helium rain. That's going to happen somewhere between 10 and 15,000 kilometers deeper. And then we really reach the places that we talked about before, the dilute core, maybe half the size or less. And we talked before, also kind of possibly a small rocky core at the very, very, very interior.
I mean, it's fascinating that your instruments can actually take you to the outer edge of the core.
Yeah, so it's the combination of the instruments. So we have instruments measuring, if I go again from the outside to the interior. From the outside, we're looking at infrared images, Juno, which is visible images, and then we have the microwave radiometer, which now is probing 6 different levels going down to, say, 100 bars. Then we have gravity, which is really sensitive to mass. So
Right.
that's only when it gets really kind of more dense. That's the next level, sensitive, say from 100 bars down to basically to the core. And then also we have the magnetic measurements. We have a magnetic very accurate measurement that we do also every orbit, and this is where the magnetic field is important. So this is sensitive to where the conductivity rises, like I mentioned before, 4,000 kilometers and deeper into the planet. So it's the set of instruments on Juno from the top all the way to the bottom that can really give us this combined information about everything.
Well, thank you so much for your time. Fascinating. And good luck. We look forward to getting more data from this mission.
Thanks a lot.